What if I told you that time isn't constant and space isn't empty, that the very fabric of our universe behaves in ways that defy everything we experience in our daily lives? We're about to embark on a journey through some of the most mind-bending realities of space-time, exploring 30 astonishing facts that will completely transform how you perceive existence itself. From the mysterious depths of black holes to the strange stretching of time itself, we'll uncover cosmic secrets that even puzzled the greatest minds like Einstein. Imagine standing on a planet where a single day lasts longer than an entire human lifetime, or gazing into a region of space so dense that not even light can escape its grasp. These aren't just science fiction concepts, they're real phenomena occurring right now in our universe, challenging our fundamental understanding of reality. The rules we take for granted here on Earth begin to warp and bend when we venture into the cosmic scale, revealing a universe far stranger and more wonderful than we could ever imagine. This exploration will take us through the most extraordinary aspects of space-time, each fact building upon the last to paint a complete picture of our incredible cosmos. You'll discover how time itself can slow down or speed up depending on gravity and motion, how empty space isn't really empty at all, and how the universe holds mysteries that continue to baffle even the most brilliant scientists today. So settle in and prepare to have your mind expanded as we journey through 30 of the most astonishing facts about space-time, each one more incredible than the last. Our journey begins with one of the most fundamental and startling truths of the cosmos. Time itself is not a constant, universal tick of a clock. It's a fluid, malleable dimension that can be stretched and slowed by the presence of mass. This isn't a theoretical abstraction, it's a daily reality that requires constant correction for one of our most common technologies, the global positioning system. Each GPS satellite orbiting our planet is in essence a highly accurate clock hurtling through space. But according to Einstein's theory of general relativity, the immense gravity of Earth warps the fabric of space-time around it. This warping has a direct effect on time, causing it to pass more slowly for an observer closer to a massive object. For the satellites which are further from Earth's gravitational pull, time actually runs faster than it does for us on the surface. If we didn't account for this, the entire system would fail within minutes. The clocks on the satellites would gradually fall out of sync with the clocks on the ground, introducing errors that would compound each day, making your navigation increasingly unreliable. Engineers must program these satellites to intentionally tick a little slower before launch, so that once they experience the weaker gravity in orbit, their clocks synchronize perfectly with ours. This is a brilliant, practical application of one of physics' most profound concepts. But to truly grasp it, we need to visualize space-time not as separate entities, but as a single, interconnected fabric. Picture a stretched rubber sheet perfectly flat. Now place a heavy bowling ball in the center. The sheet curves and dips under its weight. This is what a planet or star does to the fabric of space-time. Any object moving near that curve will have its path altered. This is what we experience as gravity, but the warping also affects time. A clock placed near the deep well of the bowling ball would tick more slowly compared to a clock out on the flat, undisturbed edge of the sheet. This time dilation effect, as it's called, becomes exponentially more dramatic near objects far more massive than our planet. Imagine a future where we could observe a clock on the surface of a neutron star, an object so incredibly dense that a single sugar cube-sized amount of its material would weigh billions of tons. There, under such unimaginable gravity, time would crawl at a relative snail's pace. An hour for that clock might equate to 100 years for a distant observer. This profound revelation shatters our everyday perception of time as a steady, unchanging river. It reveals a universe where time is a current, flowing at different speeds depending on the depth of the gravitational landscape it's moving through. And if the gravity of a neutron star seems extreme, it pales in comparison to the ultimate masters of cosmic distortion, black holes. These are regions where so much mass is compressed into such an infinitesimally small point that the gravitational pull becomes literally inescapable. The fabric of space-time isn't just warped here, it's twisted and torn into a one-way street toward a point of infinite density known as a singularity. At this incomprehensible center, our current understanding of physics completely breaks down. The equations of general relativity predict an infinity, which in the world of physics is often a sign that a theory has reached its limit, signaling the need for a new, deeper understanding that unifies gravity with quantum mechanics. The boundary surrounding this point of no return is called the event horizon. It's not a physical surface but a mathematical threshold. Think of it like a waterfall. If you're in a boat, you can paddle away from the current safely until you cross a certain invisible line. Once you go over the edge of the falls, however, the pull of the water becomes unstoppable. The event horizon is that edge for a black hole. Cross it, and every possible path forward in time leads irresistibly downward into the singularity. Not even light has a trajectory that points back out. For an outside observer, something truly bizarre appears to happen at this boundary. If we were to watch a clock, or more tragically, a spaceship, fall toward a black hole, we would see its signals slow down dramatically as it approaches the event horizon. The light from it would redden and dim, and the last tick of the clock would seem to take an eternity, frozen in time from our perspective. The object would appear to hover, fading from view without ever quite seeming to cross the line. This isn't an illusion. From our frame of reference, time for that object has effectively stopped. Yet, for the astronaut unfortunate enough to be on that ship, their own clock would seem to tick normally. They would cross the event horizon without any flashing lights or sudden jolts, at least for a sufficiently large black hole. Their perception of time remains local and personal, even as their fate from our external viewpoint is sealed and seemingly frozen forever. This stark difference in experience highlights the deeply relative nature of time itself, a reality that is both counterintuitive and profoundly beautiful in its complexity. This expansion leads us to one of the most profound and counterintuitive discoveries in all of cosmology. The universe itself is growing at an ever-increasing rate, with distant galaxies receding from us faster than the speed of light. At first glance, this seems to shatter a fundamental rule of physics, Einstein's cosmic speed limit, that nothing can travel faster than light. But the reality is far more subtle and magnificent, because these galaxies aren't racing through space. The space between us and them is itself stretching, carrying them along like raisins in a rising loaf of raisin bread. As the dough expands, the raisins move further apart. A raisin on the far side of the loaf isn't actively running away from you. It's being repositioned by the growing medium that separates you. This is precisely what is happening on a cosmic scale. The fabric of space-time is not static, it is dynamic and expanding. The more space there is between two galaxies, the more stretching occurs, meaning that over sufficiently vast distances, the cumulative effect is a recession velocity that indeed surpasses the speed of light. This doesn't violate relativity because no information, no particle, and no signal is actually traveling through space faster than light. The rule that nothing can outpace light within the cosmos remains intact. It is the stage itself that is growing, and that stage has no such speed limit. This incredible discovery of an accelerating expansion points to a mysterious force working against gravity's relentless pull. We call this force dark energy, and it is arguably the greatest enigma in modern physics. Think of the universe's expansion as a ball thrown into the air. Scientists originally expected that the mutual gravitational attraction of all the matter in the cosmos would act like gravity on the ball, slowly putting the brakes on the expansion, perhaps even eventually pulling everything back together in a big crunch. Instead, observations of distant supernova revealed that the expansion isn't slowing down at all, it's speeding up. It's as if the ball, instead of falling back to Earth, shot away into the sky with ever-increasing velocity. Dark energy is the name we give to whatever is causing this unexpected acceleration. It appears to be a property of space itself. Even in a perfect vacuum, empty space seems to contain this latent energy that exerts a negative pressure, pushing the universe apart. The more the universe expands, the more space there is, and thus the greater the effect of dark energy becomes, creating a self-reinforcing cycle of acceleration. This revelation means the ultimate fate of our universe is likely a cold, dark, and lonely one. As galaxies are pushed beyond our observational horizon, their light forever too stretched and too faint to ever reach us again. We are living in a privileged era where we can still see the cosmic landmarks of our past, but with each passing moment, the universe is quietly and inexorably fading from view. While the immense pull of a black hole represents a one-way journey into the unknown, what if there was a theoretical backdoor, a secret passage that could bypass the normal rules of the universe? This brings us to one of the most exciting and speculative ideas in all of physics, the concept of wormholes. Imagine the universe is not a flat sheet but the surface of an apple. An ant wanting to get from one side of the apple to the other has to walk the long way around the curved surface. But if a worm burrows directly through the center of the apple, it creates a much shorter, more direct tunnel. A wormhole, often called an Einstein-Rosen bridge, proposes a similar shortcut, but through the fabric of space-time itself. It would theoretically connect two distant points, potentially allowing for travel across thousands of light years in the blink of an eye, or even enabling journeys backward or forward in time. The mathematics of Einstein's theory of general relativity does not forbid such structures from existing. In fact, the equations naturally produce them as a possible solution. The most basic type is known as a Schwarzschild wormhole, but this early model presented a significant problem. It was incredibly unstable. Picture it as a tunnel made of soap film. It would form for an instant, linking 2 points, but then it would snap shut and pinch off before any piece of information, let alone a spaceship, could possibly make it through. The entrance would likely be a black hole, but the exit, known as a white hole, is a hypothetical region where nothing can enter and everything is expelled, a concept that remains entirely theoretical and unobserved in our universe. For a wormhole to ever be practical, it would need to be held open against its own tendency to collapse. This is where the science ventures into the realm of the truly exotic. Physicists like Kip Thorne have theorized that to prop open the throat of a wormhole and make it traversable, we would need a form of matter with truly bizarre properties. This so-called exotic matter would not be like anything we encounter in our daily lives. Normal matter, everything that makes up our planets and stars and ourselves, has positive energy density and exerts positive pressure, and it is gravitationally attractive. Exotic matter, by contrast, would need to have negative energy density and exert negative pressure, meaning it would be gravitationally repulsive. It would act as a kind of anti-gravity material, pushing the walls of the wormhole apart and preventing it from closing. The search for such material isn't entirely hopeless. Strange quantum effects like the Casimir effect show that on a tiny scale, certain configurations can create regions of negative energy density. In a laboratory, two incredibly smooth, uncharged metal plates placed very close together in a vacuum can actually experience a slight push toward each other. This happens because the quantum fluctuations in the vacuum between the plates are restricted compared to the fluctuations outside, creating a minute pressure difference that represents a tiny area of negative energy. While this is a fascinating demonstration of quantum weirdness, the amount of exotic matter required to stabilize a wormhole large enough for a person would be astronomical, far beyond anything we can currently conceive of creating or finding. Beyond the sheer engineering challenge, wormholes introduce fascinating and complex paradoxes, the most famous being the potential for time travel. If one end of a wormhole were moved at a significant fraction of the speed of light or placed near an intense gravitational field, time would pass more slowly for that end relative to the stationary end, an effect we know happens from general relativity. This would mean that entering the moved end would allow you to exit the stationary end at a point in time before you even entered. This scenario immediately raises the specter of the grandfather paradox, where a time traveler could potentially prevent their own grandfather from meeting their grandmother, thus preventing their own birth and creating a logical inconsistency that seems to violate the fundamental laws of cause and effect. Whether the universe has a built-in mechanism to prevent such paradoxes, perhaps through quantum mechanics or some unknown law of physics, remains one of the most captivating unanswered questions. While wormholes remain firmly in the realm of theory and science fiction for now, their study pushes the boundaries of our understanding. They force us to confront the deepest questions about the nature of reality, causality, and the possibility that the cosmos might be filled with hidden connections, a labyrinth of shortcuts waiting to be discovered if we can only learn the rules to navigate them. While the extreme gravity of black holes creates a powerful form of time dilation, there is another, more subtle effect that is constantly at work much closer to home, one that even affects the astronauts living and working right above our heads. According to Einstein's special theory of relativity, time is also stretched and slowed by motion itself. The faster you travel through space, the slower your clock ticks relative to someone who is stationary. This means that the high-speed orbit of the International Space Station literally sends its crew into the future ever so slightly. The station hurtles around the Earth at an astounding speed of roughly 28,000 kilometers per hour. At this velocity, while the effects are minuscule, they are absolutely real and measurable with incredibly precise atomic clocks. For a typical 6-month mission aboard the ISS, an astronaut will actually experience about 0.005 seconds less time than everyone on Earth. They return to our planet having aged slightly less, a genuine, if tiny, time traveler from our own future. This phenomenon occurs because of a fundamental trade-off in our universe between time and space. Einstein revealed that we don't live in a universe with 3 dimensions of space and 1 separate dimension of time, but in a single, interwoven 4-dimensional fabric called space-time. Every object is always moving through this combined fabric at the speed of light. This might sound strange, but think of your total velocity as being allocated in 2 directions, through space and through time. If you are standing perfectly still, all of your motion is directed through the dimension of time. You are rushing into your future at the maximum rate of 1 second per second. But the moment you start moving through space, you must borrow some of that velocity from your motion through time. The faster you move through space, the slower your progress through time becomes, ensuring your total speed through space-time always remains constant at the cosmic speed limit. To put this into a more tangible perspective, consider the incredible journey of a Russian cosmonaut named Gennady Padalka. Over the course of his career, he spent a combined 879 days in orbit. All that time spent traveling at high velocity added up, and thanks to the effects of special relativity, he actually experienced 8,978 full seconds less than the rest of us on Earth. That means he returned to our planet nearly 2.5 hours younger than if he had never left. This isn't a biological quirk or a result of low gravity. It is a direct and inevitable consequence of the fundamental structure of the universe, a literal slowing of time itself for the moving object. However, there's a fascinating gravitational twist to this story. While their high speed makes astronauts' clocks run slower, the ISS is also further from Earth's gravitational well than we are on the surface. As we learned from general relativity, weaker gravity makes time run faster. So, the special relativity effect of their speed works to slow their time down, while the general relativity effect of their altitude works to speed their time up. In low Earth orbit, these two effects are in competition with each other. For the space station's altitude, the gravitational effect wins by a very small margin. This means that overall, an astronaut's time actually passes a tiny bit faster than ours on the ground, counteracting some of the slowing from their speed. The net result is still a slowing of time, but the calculation becomes a delicate balance between these two incredible pillars of modern physics. A daily demonstration that Einstein's universe is not just a theoretical wonder, but a practical reality shaping our exploration of the cosmos. But if the very fabric of space-time can be warped by mass and stretched by expansion, then it must also be capable of moving, of vibrating like the skin of a drum. This brings us to a prediction so extraordinary that it took a century to confirm. Space-time itself can carry ripples known as gravitational waves. Imagine the universe not as a static stage, but as a vast, flexible membrane. When a truly cataclysmic event occurs, like two black holes locked in a final, deadly dance, they don't just orbit each other quietly. As they spiral inward at a significant fraction of the speed of light, their immense masses whip the fabric of space-time around them, sending out distortions that spread across the cosmos at the speed of light. These are not waves in space like light or sound. They are waves of space itself, rhythmic contractions and expansions of the distances between everything. For decades, these waves remained a beautiful but unproven consequence of Einstein's theory. The problem was their incredible weakness. By the time these ripples from a distant cosmic catastrophe travel across billions of light years to reach us, their effect is almost unimaginably tiny. They might change the distance between the Earth and the Sun by merely the width of a single atom. Detecting such a minuscule distortion seemed like a fool's errand, requiring technology that bordered on magic. This is where one of the most ambitious experiments in human history comes in: the Laser Interferometer Gravitational Wave Observatory, or LIGO. Its design is a masterpiece of precision, consisting of two immense L-shaped facilities located thousands of kilometers apart in the United States. Each arm of the L is a vacuum tube 4 kilometers long. Here's how it works. A single laser beam is split in two, with each half sent racing down one of the long arms. At the end, they hit perfectly polished mirrors and bounce back to recombine. Under normal conditions, the beams are tuned so that they cancel each other out and the detector sees darkness. But if a gravitational wave passes through the Earth, it does something profound. It literally stretches space in one direction and squeezes it in the perpendicular direction. For a fraction of a second, one arm of the LIGO detector becomes ever so slightly longer while the other becomes ever so slightly shorter. This minute change, smaller than 1/10,000th the diameter of a proton, alters the travel time of the laser beams just enough that they no longer perfectly cancel out when they recombine. A flicker of light appears in the darkness. That flicker is the signature of the universe ringing like a bell. On September 14, 2015, after decades of development and refinement, both LIGO detectors in Washington and Louisiana recorded an identical signal. The data showed the characteristic chirp of two black holes, each about 30 times the mass of our Sun, spiraling together and merging in a galaxy far, far away, over 1.3 billion years ago. The event released more power in gravitational waves than all the stars in the observable universe combined put out in light at that moment. Yet by the time it reached us, it only jiggled LIGO mirrors by a subatomic amount. This detection wasn't just a confirmation of a theory. It was the opening of an entirely new window on the cosmos. For all of human history, every single thing we learned about the universe came from studying light, from visible starlight to radio waves to X-rays. But now we can listen to the universe as well, hearing the vibrations of space-time itself caused by the most violent and energetic events imaginable. Since that first historic detection, LIGO and its international partners have listened to the collisions of neutron stars, events so powerful they forge gold and platinum and scatter these heavy elements across the galaxy. We are no longer just silent observers of the cosmic pageant. We have front-row seats to the symphony of space-time, each ripple telling a story of gravity operating at its most extreme. This new era of gravitational wave astronomy allows us to probe the dark, silent collisions that emit no light, revealing a universe that is far more dynamic and violent than we ever could have seen with telescopes alone. This radical reimagining of time comes from a concept in Einstein's relativity known as the block universe theory, and it proposes that the past, present, and future are not a sequence of events that come into being and then vanish. Instead, all of time, every event that has ever happened or ever will, exists simultaneously in a single, vast, four-dimensional structure. We perceive time as a river flowing from the past through the present and into the future, but according to this view, that flow is an illusion of our consciousness. In reality, the entire history of the universe is fixed, much like the entire length of a film already exists on a reel. We are simply watching it play out frame by frame, mistaking our current moment for the only thing that is real. To truly grasp this, we need to think of time as a dimension, just like the three dimensions of space. When you look at a chair in a room, you don't believe only one leg of the chair is real at any given moment. The entire chair exists with its height, width, and depth all present at once. The block universe theory suggests that time is simply another one of these dimensions. Your birth, you reading this sentence right now, and every future moment of your life all coexist in this four-dimensional block, eternally fixed in their respective positions. This means that the dinosaur era isn't gone. It's simply located in a different region of the space-time continuum, just as real as today, just not where we are currently focused. This challenges one of our most fundamental experiences, the feeling of a moving now. Our conscious awareness feels like a spotlight scanning across the timeline of the universe, illuminating the present moment. But in the block universe, there is no privileged now. What you call the present is merely your location within the time dimension. An observer near a distant star, millions of light years away, would have a completely different present moment based on their frame of reference. Your present and their present are equally valid, just as your here and their there are equally real in space. This eliminates any universal concept of the present, suggesting that our perception of time's passage is a biological and psychological phenomenon, not a fundamental feature of the physical world outside our mind. This idea finds its roots in the mathematics of relativity, where space and time are woven together into the single fabric of space-time. In the equations that describe the universe, time is treated as a coordinate, much like a latitude or longitude on a map. There is no equation that singles out a special point called now. The laws of physics, as we currently understand them, are symmetric in time. They work just as well going forward as they do backward. This doesn't mean we can reverse cause and effect, but it does imply that the entire timeline is laid out in a single, coherent structure. The future is not some undetermined possibility waiting to be chosen. It is already written into the geometry of the cosmos, as fixed and real as the past. This can feel deeply unsettling, as it seems to challenge our notions of free will and the openness of the future. If everything is predetermined, do our choices matter? Many physicists argue that this is a misinterpretation. They suggest that the block universe doesn't eliminate free will. It simply redefines it. Your choices, your thoughts, and your actions are all real and integral parts of the four-dimensional structure. The you that made a decision in the past is just as real as the you that will make a decision in the future. The entire timeline includes the complex chain of cause and effect that constitutes your life. In this view, free will is the process of the universe unfolding along a path that is inherently determined by all the events within it, including your own reasoning and desires. It's not that the future is set in stone despite us, but rather because of us. While this remains a topic of intense philosophical debate, the block universe offers a profoundly elegant and powerful way to understand reality. It resolves the strange relativistic effects of time dilation, not as distortions of a universal clock, but as natural consequences of different observers slicing the four-dimensional block at different angles. It provides a framework where the entire, magnificent history of the cosmos can be seen as a single, unchanging, and complete work of art. We are not simply watching the film, we are permanent characters within it, experiencing our story one moment at a time, while the entire masterpiece exists all at once. Yet for all the apparent stillness of the void, the seemingly empty vacuum of space is, according to our most fundamental laws of physics, a seething, bubbling cauldron of activity. This leads us to one of the most bizarre and counterintuitive facts of all. A perfect vacuum, the very definition of nothingness, is not empty. At the tiniest imaginable scales, governed by the strange rules of quantum mechanics, empty space is alive with a frantic dance of energy. This isn't just theoretical, it has real, measurable consequences that shape the very fate of our entire universe. This bizarre phenomenon is known as quantum fluctuation. At the heart of quantum mechanics lies the Heisenberg uncertainty principle, which tells us that on a subatomic level there is a fundamental trade-off. We cannot know both the exact energy of a system and the exact time for which that energy exists with perfect precision. This uncertainty opens a tiny, temporary loophole in the laws of conservation of energy. For unimaginably brief moments, pairs of virtual particles, a particle and its antiparticle, can spontaneously pop into existence, borrowing energy from the vacuum itself. They exist for a sliver of a second before they inevitably collide and annihilate each other, paying back the energy loan and vanishing without a trace. We can never directly observe these virtual particles as their existence is too fleeting, but we can see their shadow, their undeniable fingerprint on the universe. One of the most stunning pieces of evidence is the Casimir effect, which we can actually demonstrate in a laboratory. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum only a few nanometers apart, something remarkable happens. The empty space between the plates is so narrow that it can only accommodate virtual particles with very short wavelengths. However, the space outside the plates can host fluctuations of all wavelengths. This difference in activity creates a subtle pressure, literally pushing the plates together. It's a measurable force generated not by any field or particle we can see, but by the restless energy of apparently nothing at all. This ceaseless creation and destruction might seem like a weird subatomic sideshow, but its implications are cosmic in scale. Physicists believe this vacuum energy, this background hum of the universe, might be the very engine behind the accelerating expansion we call dark energy. Think of it this way: every cubic centimeter of empty space everywhere in the universe is constantly generating this tiny amount of repulsive energy. Now multiply that by the immense, incomprehensible volume of the entire cosmos. That cumulative effect could be the negative pressure that is relentlessly pushing galaxies apart faster and faster. The vacuum's microscopic frenzy could be driving the universe's ultimate fate. However, this elegant idea runs into a colossal problem, the worst prediction in all of theoretical physics. When scientists attempt to calculate the amount of energy this quantum frenzy should contribute, the math gives an answer that is absurdly, catastrophically large. We're talking about a number followed by 120 zeros larger than the value we actually observe from measuring the universe's expansion. This staggering discrepancy of 120 orders of magnitude means that if the quantum vacuum energy were that strong, the repulsive force would have blown the universe apart in the first fraction of a second of its existence, instantly tearing apart every atom, molecule, and star before any of it could ever form. The fact that we exist at all means our understanding is profoundly incomplete. This immense gap between prediction and reality is not a failure. It is a blazing signal that we are on the verge of a monumental breakthrough. It tells us that somewhere there is a deeper theory waiting to be discovered, one that will likely unite quantum mechanics with general relativity into a theory of quantum gravity. This future theory might show us how these wild quantum fluctuations cancel each other out in just the right way to leave the subtle yet powerful dark energy we detect. The silent vacuum of space is shouting a secret to us, and we are only just beginning to learn how to listen. Its apparent emptiness is the greatest illusion of all, hiding a fundamental activity that is quite literally creating the future of everything. Yet this universal speed limit, as absolute as it seems, leads to some of the most mind-bending consequences in all of physics for any object that dares to approach it. As an object moves faster and faster through space, its journey through time slows down dramatically, a phenomenon we call time dilation. Imagine two twins, one stays on Earth while the other embarks on a journey to a distant star in a spaceship traveling at 90% the speed of light. For the astronaut twin, the trip might feel like it only takes a few years, but upon returning to Earth, they would step out to find that decades or even centuries have passed for everyone they left behind. Their clock literally ticked slower due to their incredible velocity, making them a genuine time traveler into the future, but that's only half the story. The universe also contorts the very dimensions of the speeding object itself through an effect known as length contraction. From the perspective of a stationary observer, an object rushing toward them at a significant fraction of light speed would appear to be compressed or squashed in its direction of travel. A perfect meter-long ruler flying past you at near light speed would look like it's only a few centimeters long. This isn't an optical illusion. Space itself is being warped by the relative motion. For the astronaut on that high-speed ship, however, everything would appear normal inside their own reference frame. It is the rest of the universe that would seem to be contracting and warping around them. These bizarre effects are not flaws or errors in the cosmos. They are essential, elegant features that maintain the consistency of physical laws for all observers. They ensure that no matter how fast you are moving, you will always measure the speed of light to be the same constant value. This principle forces the universe to bend time and space to keep its ultimate speed limit inviolate. The energy required to push even a single particle to the speed of light becomes infinite, an impossible barrier that preserves causality and the very logical structure of reality, ensuring that cause always precedes effect and the universe remains a coherent, predictable place. We've seen how time can be warped and stretched, but this leads to one of the most profound questions of all. Did time itself have a beginning? The overwhelming consensus from our current understanding of physics points to a definitive yes. According to the standard model of cosmology, the universe and everything in it, including the very fabric of space and time, exploded into existence from a single point of infinite density and temperature roughly 13.8 billion years ago. This event, the Big Bang, marks the ultimate origin of our cosmic clock. To truly grasp this, we need to consider the nature of the Big Bang singularity. This wasn't an explosion in space like a cosmic bomb going off in a pre-existing void. It was the simultaneous emergence of space itself, time itself, and all matter and energy all at once from a state where our current laws of physics completely break down. The equations of general relativity predict that at this point the curvature of space-time becomes infinite. This means that if we could rewind the cosmic film all the way back, we would see the entire observable universe compressed into an infinitesimally small, infinitely hot, and infinitely dense point. At this singularity, the concepts of before and after cease to have any meaning because time, as a dimension, did not yet exist. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question itself is a category error based on a framework that no longer applies. This doesn't mean scientists are content to simply say, "And then a miracle happened." Several compelling theories attempt to peek behind the veil of the initial singularity. One of the leading ideas is cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the universe underwent an unimaginably rapid exponential expansion, doubling in size perhaps 100 times or more in less than a trillionth of a second. This inflationary period would smooth out the universe, creating the remarkably uniform conditions we observe in the cosmic microwave background radiation. Crucially, inflation may itself be eternal. Some models suggest that while inflation ended in our region of the universe, giving rise to the stars and galaxies we see, it continues forever in other regions, constantly spawning new, bubble universes within a greater multiverse. In this breathtaking scenario, our Big Bang was not the absolute beginning but simply the moment our particular bubble of space-time formed. Another fascinating approach comes from quantum gravity theories like loop quantum gravity, which attempt to marry general relativity with quantum mechanics. These models suggest there may not have been a singularity at all. Instead, the universe could be a cyclical entity or could have arisen from a previous state of collapse. In loop quantum cosmology, for instance, the immense gravity of a collapsing universe doesn't lead to a point of infinite density, but instead reaches a point of maximum compression and then bounces back outward, triggering a new expansion phase. This big bounce model elegantly avoids the problematic singularity by replacing it with a transition from a previous cosmic era, meaning time could, in a sense, extend backwards indefinitely. Perhaps the most mind-bending proposal is the no-boundary conjecture put forward by physicists like James Hartle and Stephen Hawking. They applied the strange rules of quantum mechanics to the universe as a whole. In the quantum world, particles don't have single, definite paths. They have a probability of taking every possible path. Hartle and Hawking suggested that if we treat the entire history of the universe as a quantum particle, then its path must include a state where time behaves like space. In their model, if you go back far enough, the familiar dimension of time smoothly transforms into a fourth dimension of space. This creates a finite universe without any sharp, singular beginning, a geometry that is closed and curved, much like the surface of a sphere. The Big Bang, in this view, becomes the south pole of this space-time globe. There is nothing south of the South Pole, yet the surface itself is perfectly well-defined and finite. There is no boundary, no moment of creation, just a smooth, self-contained geometry where the question of a before dissolves into the curvature of reality itself. Each of these theories offers a different profound answer to the mystery of our cosmic origin, from a definitive beginning to an eternal cycle to a universe without any edge in time at all. They all share one common thread. They push the boundaries of human comprehension, challenging us to think in ways far beyond our everyday experience of a linear, flowing time. The origin of time remains one of the ultimate frontiers of science, a question that sits at the precipice of what is knowable, reminding us that the universe is far stranger and more wonderful than we could ever imagine. Even light itself, which has no mass, can bend the very fabric of space-time. This astonishing fact emerges directly from the heart of Einstein's general relativity, which tells us that gravity is not a force generated by mass alone, but a curvature of space-time caused by the presence of energy and momentum. Since light, carried by particles called photons, possesses energy, it must also generate its own tiny gravitational field and warp the space around it. The amount of warping is incredibly small, but the principle is revolutionary. Everything that contains energy, from a massive star to a massless beam of light, interacts with and distorts the cosmic stage. The most spectacular demonstration of this principle is a phenomenon called gravitational lensing. Imagine a massive object like a galaxy cluster sitting between us and an even more distant galaxy. The immense energy and mass of the cluster create a deep well in space-time. When light from the background galaxy travels toward us, its path isn't a straight line. It follows the curved geometry of this warped region. From our perspective, the light of the distant galaxy is bent around the foreground cluster. This cosmic trick of the light doesn't just slightly shift the galaxy's position. It can dramatically distort its image, stretching it into long, faint arcs or even creating multiple mirrored copies of the same object, arranged in a perfect circle or cross pattern known as an Einstein ring. This isn't just a theoretical curiosity, it's a powerful tool used by astronomers. By analyzing how the light is distorted, we can essentially use these natural telescopes to map the distribution of mass in the lensing cluster, including the mysterious dark matter that we cannot see directly. It allows us to peer further back in time than ever before, magnifying the faint glow of the universe's first galaxies. Gravitational lensing turns the entire cosmos into a vast funhouse of mirrors, but instead of creating illusions, it reveals profound truths about the weight and structure of the universe, all made possible by the fact that even the ephemeral energy of light leaves its own indelible mark on the shape of reality. But for all the ways that physics allows time to be bent and slowed, there is one aspect of it that remains stubbornly fixed and absolute in our experience: its direction. We remember the past but not the future. We are born, we age, we die. A cup of coffee cools to room temperature. It never spontaneously heats up. This relentless one-way flow is known as the arrow of time, and it stands in stark contrast to the time-symmetric laws of physics themselves. The equations governing particles work just as well running forward as they do backward. So why does our macroscopic reality have such a powerful and undeniable preference for one direction? The most compelling answer comes not from relativity or quantum mechanics, but from thermodynamics, specifically the second law. This law states that in any closed system, the total entropy, which is a measure of disorder or randomness, will always increase over time. It will never decrease. Think of entropy as a measure of how spread out energy is. A cup of hot coffee has all its heat energy concentrated in one place. It's a state of low entropy. As it sits on the table, that heat energy dissipates into the room, spreading out until everything is the same lukewarm temperature. This is a state of high entropy. The energy hasn't disappeared, it's just become more disordered and less useful. The process is irreversible. All the scattered air molecules in the room are incredibly unlikely to suddenly coordinate their motion, gather their energy, and zoom back into the coffee cup to reheat it. This inevitable march toward disorder gives time its arrow. The reason we perceive time as moving forward is because we are constantly observing the universe progressing from states of lower entropy to states of higher entropy. Our very memories rely on this principle. Forming a memory in your brain is a physical process that creates a specific, ordered structure, and that process increases the overall entropy of the universe by releasing a tiny amount of heat. Recalling a memory doesn't reverse that entropy increase. This is why we have records of the past, a photograph, a history book, a fossil, but not of the future. Those records are themselves low-entropy islands created at the cost of a greater increase in disorder elsewhere. This deep connection between time and entropy pushes our inquiry back to the very beginning of everything. Why does time have a direction? Because the universe started in a state of incredibly low entropy. The Big Bang presents us with the ultimate mystery. Why was the early universe so astonishingly ordered? All the matter and energy of the cosmos was packed into an ultra-hot, ultra-dense, but remarkably smooth and uniform state. This was a condition of exceptionally low entropy. Since that moment, the universe has been doing what any system does when it starts in such an unlikely configuration. it has been relaxing, expanding, and evolving toward a state of maximum disorder. We are all, in a very real sense, living in the aftermath of that highly ordered beginning, riding the wave of increasing entropy into the future. The ultimate fate of the universe appears to be a state known as heat death, a bleak but fascinating endpoint. After trillions upon trillions of years, the expansion of the universe will have carried all galaxies beyond each other's observable horizons. Stars will have burned out, black holes will have slowly evaporated through Hawking radiation, and all matter may eventually decay into radiation. The cosmos will become a vast, cold, and incredibly dilute soup of particles and energy, evenly distributed throughout an ever-expanding void. In this state, entropy has finally reached its maximum value. There are no more temperature differences to drive engines, no more concentration of energy to create structure, and no more processes that can occur. With no further increase in disorder possible, the arrow of time itself may cease to have any meaning. The universe will be static, eternal, and featureless. The cosmic clock will have effectively stopped, not with a bang, but with the faintest, coldest whisper imaginable. While the effects of time dilation are subtle for astronauts, they become truly transformative at much higher velocities. Traveling to the future isn't just a science fiction trope. It's a guaranteed outcome of Einstein's special relativity, a one-way ticket that requires nothing more than extreme speed. The faster you move through space, the slower you move through time relative to a stationary observer. To make a significant leap forward, you would need to build a spacecraft capable of traveling at a significant fraction of the speed of light. Imagine accelerating away from Earth on a journey to a nearby star and back. For you on the ship, the trip might only take a few years of your personal time. But due to the relentless math of time dilation, when you return to Earth, you would find that decades or even centuries had passed for everyone you once knew. You would have effectively traveled into their future, a living relic of a bygone era. The most famous illustration of this is the twin paradox. One twin remains on Earth while the other embarks on a high-speed cosmic voyage. Upon the traveling twins' return, they are significantly younger than their Earth-bound sibling. This isn't a paradox in the true sense because the situation isn't symmetric. The twin on the spaceship experiences acceleration to turn around and come home, breaking the symmetry of inertial motion and confirming that they were the one who truly went on the journey. Their experience of less time is absolute. We even see a microscopic version of this in our largest particle accelerators. When we smash particles like muons into each other at 99.9% the speed of light, their internal clocks slow down so dramatically that they exist long enough to reach the detectors, whereas if they were at rest, they would have decayed into other particles long before. We are, in a very real sense, briefly hurling them a tiny distance into the future. Gravity offers another, even more powerful method for future time travel. As we've explored, time runs slower in stronger gravitational fields. Positioning yourself just outside the event horizon of a supermassive black hole would place you in one of the most intense gravitational environments in the universe. There, time for you would crawl almost to a standstill relative to the rest of the cosmos. You could orbit for what feels like just a few hours and then return to find that thousands of years had passed for the universe you left behind. This method doesn't require the complex acceleration and deceleration of a near-light-speed journey. It simply requires surviving the immense tidal forces and other perils of hovering at the edge of oblivion. Both methods offer a clear, physics-backed path to the future, a journey from which you could never return to your own time, but would instead arrive in a world that has moved on without you. This elegant fusion of dimensions into a single entity is what we mean when we talk about the fabric of space-time. It's not just a poetic metaphor, it's the foundational bedrock of Einstein's general relativity. In our everyday lives, we are intimately familiar with the three dimensions of space. We can move forward and backward, left and right, up and down. These directions define the stage upon which everything happens. But Einstein's brilliant insight was to realize that time is not a separate, universal metronome ticking in the background. Instead, it is interwoven with those three spatial dimensions, creating a four-dimensional continuum. Every event in the universe, from a supernova explosion to you reading this sentence, has a specific location not just in space but in time as well. This four-dimensional address is an immutable part of reality. This new understanding completely redefines our conception of gravity. For centuries since Newton, we thought of gravity as a mysterious force that acted instantaneously across vast distances, pulling objects like the Earth and the Moon together. But in Einstein's universe, gravity isn't a force in the traditional sense at all. Instead, it is the result of the curvature of this four-dimensional space-time fabric. Mass and energy tell space-time how to curve, and the curvature of space-time, in turn, tells mass and energy how to move. A common analogy is to picture space-time as a taut, flexible rubber sheet. If you place a heavy bowling ball in the center, it creates a deep dimple. Now, roll a marble across the sheet. Instead of traveling in a straight line, its path will curve inward, following the contour created by the bowling ball. The marble isn't being pulled by a mysterious force. It's simply following the most direct path through the curved geometry it finds itself in. In our solar system, the Sun is that bowling ball. Its immense mass creates a profound curvature in the space-time around it. The planets, like the marble, are simply following the straightest possible paths through this curved geometry. These paths are called geodesics, and from our limited three-dimensional perspective, they appear as the elliptical orbits we observe. This explains phenomena that Newtonian gravity struggled with, such as the precise orbit of Mercury. Its path isn't a perfect ellipse because space-time near the Sun is so curved that the ellipse itself slowly rotates or precesses over time. General relativity predicted this exactly, providing stunning confirmation that we live in a four-dimensional universe where the stage itself is dynamic and malleable. This curvature affects not just the paths of objects, but the very nature of time itself, which is why we must always consider space and time together. A clock placed in a stronger gravitational field, deeper within the curvature created by a planet or a star, will tick more slowly than a clock in weaker gravity. This is why time runs slightly faster for a GPS satellite in orbit than it does for us on the surface of the Earth. The satellite is higher up in a region of space-time that is less curved by Earth's mass. If the onboard computers didn't constantly correct for this relativistic time dilation, the entire system would give inaccurate positions within minutes. Our most advanced navigation technology is at its heart a practical application of the fact that we live in a four-dimensional space-time continuum where gravity is geometry. But if the universe is a seamless fabric of space and time, then how can two particles possibly communicate across that fabric faster than light, seemingly ignoring the very rules of the stage they exist upon? This brings us to a phenomenon so strange that it troubled Einstein himself, a quantum connection that appears to ghost through the cosmos without any regard for distance. It's called quantum entanglement, and it represents one of the most profound mysteries in all of physics, challenging our very understanding of locality and reality. To understand entanglement, we must first step into the bizarre world of the very small. In quantum mechanics, particles don't have definite properties like spin or polarization until they are measured. Instead, they exist in a fuzzy cloud of all possible states simultaneously, a condition known as a superposition. Now, imagine we have a special process that creates two particles and sends them flying off in opposite directions. Because they were born from the same quantum event, their fates are linked. Their properties remain undetermined and intertwined. They are described by a single, shared quantum state. It's not that each particle has a hidden, set value. It's that the two particles are a single system, no matter how far apart they travel. this is where the magic and the profound unease begins. Let's say we measure one of these entangled particles and find it has a certain spin, say up. At that exact instant, its partner, which could be on the other side of the galaxy, will instantly resolve itself into the perfectly correlated state down. The act of measuring one particle seems to force its distant twin into a specific, opposite condition, all without any signal passing between them. This instantaneous correlation appears to violate the cosmic speed limit set by the speed of light and defies our classical intuition about how cause and effect should work across space-time. Einstein famously derided this as spooky action at a distance, arguing that it pointed to a flaw in quantum theory, suggesting there must be some hidden variables, some deeper layer of reality that predetermined the particle's states all along, making the connection seem spooky when it was really just preordained. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised an ingenious mathematical test, now known as Bell's theorem, to determine who was right. Bell's inequality set a clear boundary. If local hidden variables existed, if everything was predetermined as Einstein hoped, then the results of certain measurements would stay below a specific value. If quantum mechanics was correct and this spooky action was real, the results would exceed that value. When scientists finally performed these delicate experiments, the results were unequivocal. Quantum mechanics won. Entangled particles consistently violated Bell's inequalities, proving that their connection is real and instantaneous. There are no hidden local variables. The universe is genuinely spooky. This doesn't mean we can use entanglement to send information faster than light, which is a crucial distinction. The correlation between the particles may be instantaneous, but it is also completely random. The person measuring the first particle has no control over whether they get an up or a down result. The person with the second particle just sees a random outcome. It's only when the two experimenters later get together and compare their notes that they can see the perfect, spooky correlation. Until that comparison is made via a normal, light speed-limited communication channel, neither side sees anything but randomness. So, while the link is instantaneous, it cannot be used to send a message, preserving Einstein's cosmic speed limit for information and preventing paradoxes. The implications of this are staggering for our understanding of reality. Entanglement suggests that at a fundamental level, the universe may not be made of separate, independent objects. Instead, it might be a deeply interconnected whole, where the properties of one particle are only defined in relation to another, regardless of the space between them. This challenges the very idea of locality, the principle that objects are only influenced by their immediate surroundings. It paints a picture of a universe where space itself might be an emergent property, a derived concept that arises from a vast, underlying network of quantum connections. In this view, the seemingly empty void of space-time is not the primary stage. It is the curtain that hangs over a far more complex and interconnected quantum reality, a reality where distance is an illusion and everything is fundamentally linked in ways we are only just beginning to fathom. But if the universe is built upon such strange and instantaneous quantum connections, perhaps it suggests that our perception of a solid, three-dimensional reality is nothing more than a magnificent illusion. This brings us to one of the most radical and mind-expanding ideas in modern theoretical physics, the holographic principle, which proposes that our entire three-dimensional universe, with all its stars, planets, and people, might be a projection of information stored on a distant two-dimensional surface. The seeds of this astonishing concept were first discovered not in the vastness of space, but in the study of black holes. When anything falls into a black hole, it seems to vanish forever, taking all its information with it. This presented a grave problem for quantum mechanics, which holds that information can never be truly destroyed. It can only be scrambled or rearranged. This conflict is known as the black hole information paradox. physicist Jacob Bekenstein made a breakthrough when he realized that a black hole's entropy, a measure of its hidden information, is not proportional to its volume as one might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon. This was a profound clue. It suggested that all the information needed to describe everything that had ever fallen into the black hole could be entirely encoded on the two-dimensional boundary that surrounds it, like a cosmic DVD storing a 3D movie. This idea was solidified by work from physicists like Gerard T. Hooft and Leonard Susskind, who formulated the holographic principle. They proposed that this isn't just a quirky property of black holes, it could be a fundamental feature of the entire universe. Just as a hologram on your credit card is a two-dimensional surface that creates the illusion of a three-dimensional image when you tilt it, the reality we experience might be a vast, complex holographic projection. In this view, the three spatial dimensions we move through could emerge from a network of information stored on a two-dimensional surface at the very boundary of the observable universe. To grasp this, imagine you are watching a movie on a television screen. The picture appears to have depth and movement, with characters moving toward and away from you. But you know that all of this information is actually encoded in the flat, two-dimensional array of pixels on the screen itself. The holographic principle suggests our universe operates in a similar way. The stars, galaxies, and even the space between them are the rich, three-dimensional movie we are watching. But the complete script for this movie, all the information that defines it, is written on a flat, distant surface we can never see. We are not the audience watching the screen, we are the characters inside the projection, mistaking the brilliant display for the real thing. This isn't just philosophical speculation, it has tangible consequences for the nature of reality. If the holographic principle is correct, it implies there is a fundamental limit to the amount of information any region of space can contain, and this limit is defined by its surface area, not its volume. It also suggests that space-time itself is not a fundamental building block of the universe, but an emergent property that arises from a deeper, more information-theoretic reality. The smooth continuity of space and time we experience might be a kind of approximation, much like a photograph appears smooth from a distance but reveals itself to be made of tiny, discrete pixels when you look closely. The universe, in its truest form, might be digital, a vast cosmic computation where the illusion of reality is rendered in breathtaking detail from a simpler, lower-dimensional source. While orbiting high above our planet, astronauts on the International Space Station experience a strange and constant tug of war between two of Einstein's great theories, and the outcome directly affects the flow of time itself. We've seen how their tremendous speed, as described by special relativity, works to slow their clocks down, but there's another competing effect at play, one that comes from their altitude and the principles of general relativity. Because they are further from Earth's center of mass, the planet's gravity has a weaker hold on them, and since gravity is the curvature of space-time, a weaker gravitational field means time actually runs faster for them than it does for us on the surface. This creates a fascinating relativistic competition. The astronauts' high velocity tries to make their clock tick slower, while their weaker gravity tries to make it tick faster. So which force wins? For the specific orbit of the International Space Station, the gravitational effect is actually slightly stronger. This means that, overall, time for an astronaut passes a tiny bit more quickly than it does for us on Earth. The slowing effect from their speed is still there, but it's outweighed by the speeding up effect of their higher altitude. The net result is that they still experience less time than we do, but the calculation becomes a delicate balance between these two incredible cosmic forces. To put this into a tangible perspective, let's look at the real-world numbers. The ISS orbits at about 400 kilometers above the Earth, traveling at roughly 28,000 kilometers per hour. Over a typical 6-month mission, the combined effects of special and general relativity cause an astronaut's clock to fall behind a clock on Earth by a few milliseconds. This minuscule difference is constantly measured and accounted for by the ultra-precise atomic clocks that control the GPS system, which operates at an even higher altitude. If these relativistic effects weren't programmed into the satellites from the moment they launch, the entire navigation network would become useless within a single day, with errors accumulating at a rate of about 10 kilometers per day. This daily reality for astronauts and engineers is a profound demonstration that Einstein's theories are not abstract mathematical concepts. They are active, measurable forces that shape our technology and our perception of reality. The universe has a built-in flexibility to time itself, a flexibility that depends entirely on your state of motion and your position within a gravitational field. For those who venture into the cosmos, they are literally stepping into a slightly different stream of time, a stream that flows at a subtly altered pace, proving that even in the vast emptiness of space, there is no such thing as a universal now. Yet even the bizarre notion of a holographic universe may not represent the ultimate limit of cosmic weirdness, for the very fabric of space-time might be threaded with defects, frozen scars left over from the universe's fiery birth. In the first unimaginably hot moments after the Big Bang, the universe underwent a series of profound phase transitions as it expanded and cooled. Think of steam condensing into water or water freezing into ice. During these shifts, the underlying symmetries of the fundamental forces were broken and the structure of the vacuum itself changed. And just as freezing water can trap bubbles of air or form cracks in the ice, these cosmic phase transitions could have left behind flaws in the very structure of reality. The most extraordinary of these hypothetical relics are called cosmic strings. These aren't strings in any traditional sense. Imagine a cosmic string as an infinitely long, impossibly thin crack in the universe, a one-dimensional defect where the fabric of space-time is stretched to its absolute limit. They are thought to be narrower than a proton, yet a single meter of such a string could contain more mass than all of Mount Everest, making them perhaps the most dense objects in all of existence. Their gravitational influence would be truly alien. Because of their immense density and unique one-dimensional shape, the gravity around a cosmic string wouldn't pull objects toward a central point like a planet or star. Instead, it would create a conical distortion in space-time. A useful way to picture this is to take a sheet of paper and draw a straight line from the top to the bottom. Now cut out a thin pizza slice wedge from the paper and then tape the two cut edges back together. The paper is now intact, but it's no longer flat, it has a conical shape. This is analogous to what a cosmic string would do to space. If you were to travel in a perfect circle around the string, your path would normally take you through 360 degrees and bring you back to your starting point. But because space itself is now cone-shaped, you would actually return to your starting point after traveling only 359 degrees. This missing angle means that if you look past a cosmic string, you wouldn't see just one image of a distant galaxy, you would see two. The string would act as a gravitational lens, but unlike the smooth curvature from a massive cluster, this lensing would create identical, duplicated images of anything behind it, a perfect cosmic mirage. The implications become even more astonishing when we consider their potential connection to time. The immense tension and density of a cosmic string could, under the right conditions, theoretically allow it to form closed loops. And if two strings were to cross or a single loop were to vibrate in a specific way, the resulting gravitational shockwaves could be so severe that they might literally twist the fabric of space-time into a closed time-like curve, a stable, traversable pathway into the past. This offers a potential mechanism for time travel that doesn't rely on the exotic matter needed for wormholes, using instead the raw, twisted geometry of the universe's own primordial defects. While no cosmic string has ever been conclusively observed, their potential role in the cosmos is immense. In the early universe, their vast gravitational wells could have acted as seeds for the formation of the very first galaxies, providing the initial clumps of matter around which everything else coalesced. Their vibrations would ripple through the cosmos, generating gravitational waves that we might one day detect with observatories like LIGO. The hunt for these ghosts from the beginning of time continues, a search for the cracks in reality that could hold the key to understanding not only how our universe formed, but whether the doors to its past might still be hanging open, waiting to be found. But the idea of a universe born from a single quantum fluctuation is just the beginning. What if our entire cosmos is merely one bubble in a vast, frothing ocean of universes, each with its own unique version of space and time? This is the breathtaking proposition of the multiverse, a concept that emerges naturally from our most successful theories of cosmic origins. The mechanism for this infinite creation is the same inflationary expansion that smoothed out our early universe. According to the theory of eternal inflation, once this exponential expansion begins, it may never truly stop. Instead, it continues forever in a background sea of hyper-stretched space-time. Within this endlessly inflating background, random quantum fluctuations can provide the tiny seed for a new bubble universe to spontaneously form. Think of it like a pot of water coming to a boil. The inflating background is the hot water, and each bubble that appears is a region where inflation has ended. Inside that bubble, the energy that was driving the expansion is released in a fiery burst, creating a new Big Bang and an entire universe with its own distinct physical laws. Our universe is just one of these bubbles, and because the inflating background is infinite, this process of bubble nucleation can happen an infinite number of times, giving rise to a limitless multiverse. The consequences of this are staggering. In this vast cosmic landscape, the fundamental constants of nature, the strength of gravity, the mass of an electron, the very speed of light, may not be universal truths. They could be more like local bylaws, randomly set during the phase transition that ended inflation within each individual bubble. In some universes, gravity might be so strong that stars form and burn out in an instant. In others, the weak nuclear force might be too feeble to allow for the formation of atoms at all. An infinite multiverse implies that every possible combination of physical constants and laws must exist somewhere. There could be universes where time has 2 dimensions, or where space is curled up into 11 dimensions. There could be realms where the arrow of time runs backward from our perspective, or where entropy decreases naturally, making broken cups spontaneously reassemble. This idea provides a potential solution to one of the greatest mysteries in physics. Why does our universe seem so perfectly fine-tuned for life? If the strength of the gravitational constant were even slightly different, or if the cosmological constant were a little larger, stars and planets could never have formed, and life as we know it would be impossible. In a single, lonely universe, this apparent fine-tuning seems like an incredible coincidence. But in a multiverse, it's simply a selection effect. We find ourselves in a universe with the right constants for life because, in an infinite ensemble of universes with all possible laws, we logically cannot exist anywhere else. We are living in one of the rare habitable pockets in a much larger and mostly inhospitable meta-universe. This concept pushes the very boundaries of science, as these other universes are, by their very nature, causally disconnected from our own. The space between bubbles is inflating so rapidly that no light, no signal, and no particle could ever cross the gap. We are forever isolated within our own cosmic pocket. This leads some to question whether the multiverse is even a scientific theory, as it seems to make no testable predictions. However, physicists are ingenious. If our universe ever collided with another bubble in the distant past, the immense energy of that collision could have left a permanent imprint on the cosmic microwave background radiation, a faint circular pattern that we might one day detect. While no definitive evidence has been found, the search continues, a hunt for bruises on the sky that would prove we are not alone in the metacosmos. The multiverse remains one of the most awe-inspiring ideas in all of science, suggesting that the reality we perceive is just an infinitesimal fraction of a grander, more extravagant existence, a cosmic quilt woven from an infinite variety of space-times. But this smooth, continuous fabric of space-time we've been describing might only be an approximation, a large-scale average of something far more chaotic and bizarre at its most fundamental level. When we venture down to the smallest possible scales, to the realm of the Planck length, our classical picture of reality dissolves into a seething, turbulent froth. This is the concept of space-time foam, a term coined by the legendary physicist John Wheeler to describe the violent quantum fluctuations that are thought to characterize the fabric of the universe at this unimaginably tiny scale. To understand why this must happen, we need to bring together the two great pillars of modern physics, general relativity and quantum mechanics. General relativity gives us our beautiful description of space-time as a smooth, warped continuum. Quantum mechanics tells us that on the smallest scales, nothing is ever still or definite. There is a fundamental uncertainty and a constant, frantic dance of energy. The Heisenberg uncertainty principle doesn't just apply to particles, it applies to the very fields that define space-time itself. This means that the energy content, and therefore the curvature, of a tiny region of space cannot be precisely defined. For a split second, a region could have enough energy to warp itself dramatically, and then an instant later that energy could vanish. The result is a microscopic chaos. At scales a trillion times smaller than an atom, space-time is not smooth. It is believed to be a bubbling, foamy mess constantly fluctuating. Tiny wormholes might spontaneously form, connecting 2 points for a fleeting moment before pinching off and disappearing back into the quantum vacuum. Microscopic black holes could pop into existence and evaporate almost instantly through Hawking radiation. The geometry of space-time itself is in a constant state of violent change, with the very concepts of before and after losing their clear meaning in the foam. It's as if we're looking at the surface of a calm pond from a great distance, seeing it as a smooth, glassy sheet. But if we could zoom in to the molecular level, we would see a turbulent, churning chaos of water molecules constantly jostling and moving. The foam is that molecular view of the cosmos itself. This presents a monumental challenge for physicists. The smooth, geometric language of general relativity and the probabilistic, fluctuating language of quantum mechanics are fundamentally at odds when they meet in the foam. Creating a theory of quantum gravity, a single set of rules that can describe this frenzied microscopic behavior, is the holy grail of theoretical physics. Until we have that theory, the Planck scale remains the final frontier, a domain of pure potentiality where the very notions of space and time as we know them are born from an underlying quantum chaos we are only beginning to imagine. And this constant interplay between the two pillars of Einstein's genius isn't just a theoretical curiosity, it's the very reason your phone can tell you where you are with such stunning precision. Those global positioning system satellites zipping around our planet at thousands of kilometers per hour are living through these relativistic effects every single second, and if we didn't compensate for them, the entire system would fail almost instantly. Each satellite is essentially a hyper-accurate atomic clock in orbit, and it's constantly broadcasting the exact time down to Earth. Your phone or your car's GPS receiver picks up these time signals from multiple satellites, and by calculating the tiny differences in how long each signal took to arrive, it can triangulate your exact position on the globe. The entire system relies on an exquisitely precise synchronization of time, a synchronization that the universe itself is constantly trying to disrupt. General relativity tells us that because these satellites are farther from Earth's gravitational well, time should run faster for them. The weaker gravity at their altitude means their clocks gain about 45 microseconds per day compared to clocks on the surface. But then, special relativity chimes in with the opposite effect. Because the satellites are moving at such high orbital speeds, their velocity relative to us on the ground makes their clocks run slower, losing about 7 microseconds per day. It's a constant tug of war between the two theories. When you do the math, the gravitational effect from general relativity is stronger, so the net result is that the satellite's clocks gain a total of about 38 microseconds each day. That might sound vanishingly small, 38 millionths of a second, but in the world of precision navigation, that tiny error is absolutely colossal. Because these signals are traveling at the speed of light, which is 300 million meters per second, an error in time translates directly into an error in distance. A miscalculation of just 1 microsecond would throw off your position by 300 meters. If the engineers didn't pre-program the satellite clocks to compensate for this, that daily gain of 38 microseconds would cause your phone's navigation to drift by over 10 kilometers every single day. Within just a few minutes, the system would be so inaccurate it would be utterly useless, telling you to turn left in the middle of a field instead of onto a highway exit. So before a GPS satellite is even launched, its internal clock is deliberately set to run slightly slower than normal. This pre-correction ensures that once it's in orbit, experiencing the competing pulls of velocity and gravity, its clock will tick in perfect sync with the clocks on Earth. It's a brilliant, real-world application of some of the most profound physics ever discovered, a daily demonstration that Einstein's universe isn't an abstract concept, but the very framework that makes our modern world possible. But what ultimately determines that fate? It all comes down to the shape of the entire universe, a grand geometric property that tells us whether the cosmos will expand forever, eventually collapse back on itself, or continue on a knife's edge. This isn't about the local curves created by stars and galaxies. This is about the overall global curvature of all space-time, a geometry dictated by the total amount of matter and energy within the cosmos, including the mysterious dark energy that pushes it apart. Scientists describe 3 possible shapes for the universe, each with a dramatic implication for our ultimate destiny. The first is a closed universe. Picture the surface of a sphere. If you were to launch 2 laser beams perfectly parallel to each other on this curved surface, they would eventually converge and cross. This is positive curvature. A universe with this shape would contain enough matter and energy, a density above a specific critical value, that its own gravity would eventually overcome the expansion, pulling everything back together in a final, cataclysmic event often called the Big Crunch. In this scenario, space-time itself would reverse its expansion and begin to contract, leading to a fiery and dense end. The second possibility is an open universe. Imagine the surface of a saddle curving upwards in one direction and downwards in the other. Here, those 2 parallel laser beams would diverge, forever spreading apart. This negative curvature signifies a universe with a density below the critical value. The gravitational pull of its contents would be too weak to ever halt the expansion. In this open model, the universe would continue to expand forever, but at a steadily slowing rate, gradually cooling toward the heat death we discussed earlier, a long, slow fade into darkness and maximum entropy. For a long time, cosmologists believed the fate of the universe was a simple tug of war between these 2 outcomes, a battle between the inward pull of gravity and the outward momentum of the Big Bang. But then came the shocking discovery of dark energy and the accelerating expansion, which completely upended this simple dichotomy. This led us to the third and most likely shape, based on our best observations, a flat universe. In a flat geometry, parallel laser beams remain perfectly parallel forever. The density of the universe is precisely at the critical value, and the geometry of space-time on the largest scales is Euclidean, just like the flat plane we learned about in high school geometry. This perfect flatness is deeply mysterious. Why is the density so exquisitely fine-tuned to this precise value? The theory of cosmic inflation provides a compelling answer. The violent exponential expansion in the universe's first fraction of a second would have stretched the fabric of space-time so dramatically that any initial curvature would have been smoothed out to imperceptible levels, much like inflating a balloon makes any small section of its surface appear flatter and flatter. The universe we observe is flat because inflation made it that way. However, dark energy changes the fate of a flat universe. It's no longer a question of whether gravity will slow the expansion enough to cause a collapse. The presence of dark energy means the expansion is not slowing down, it's speeding up. So a flat universe with dark energy is still destined to expand forever, but it won't be a gradual cooling. It will be a relentless, accelerating rip into the future. Galaxies will be pushed beyond our cosmic horizon, and the universe will become increasingly cold, empty, and isolated. The geometry may be flat, but the fate is a profoundly lonely and accelerating expansion, driven by the enigmatic force that makes up the majority of the cosmos's energy budget. The shape tells us the geometry, but the contents, especially dark energy, write the final chapter. While black holes represent the ultimate cosmic sink, draining matter and energy from the universe, the equations of general relativity hold the door open for a bizarre opposite, a white hole. If a black hole is a region of space-time from which nothing can escape, a white hole is its theoretical time reversal, a region into which nothing can enter. Instead of pulling everything inward toward a singularity, a white hole would violently expel all matter and energy, a cosmic geyser of infinite pressure erupting outwards from a central point. This isn't just a fanciful idea, it emerges as a mathematically valid, if highly improbable, solution to Einstein's field equations, presenting a universe that is perfectly symmetric in time. The simplest way to visualize a white hole is to imagine hitting the rewind button on a black hole. Take the entire life cycle of a star collapsing, forming a black hole, and slowly sucking in a cloud of interstellar gas. Now run that film backwards. You would see a torrent of energy and matter explosively bursting out of a single point, after which the object would simply vanish. This time-reversed symmetry is elegant in theory, but it creates a profound physical paradox. A white hole would violate the second law of thermodynamics by spewing out vast amounts of energy and matter in a highly ordered, low-entropy state, essentially acting as a source of free energy that decreases the overall disorder of the universe, which is something we never observe happening naturally. This is a major reason why most physicists believe stable, naturally occurring white holes do not exist in our universe. The arrow of time, driven by the relentless increase of entropy, seems to forbid such objects from forming after the initial low-entropy state of the Big Bang. However, their theoretical existence is crucial for one of the most tantalizing ideas in cosmology, the Einstein-Rosen bridge or wormhole. In the earliest mathematical models, a Schwarzschild wormhole was envisioned as a tunnel connecting a black hole to a white hole. The black hole would be the entrance, the tunnel the throat, and the white hole would be the exit in some other region of space or even in a different universe entirely. This seems like the perfect setup for a traversable tunnel, but the original model had a fatal flaw. The connection is incredibly unstable. The moment even a single photon enters the black hole mouth, the tunnel collapses faster than the speed of light, pinching off the bridge and leaving behind two separate singularities before any information or matter could possibly traverse it. The white hole exit in this model is also problematic, as it would have existed since the beginning of the universe, meaning any matter it ejected would have done so in the distant past, making it an unlikely candidate for practical travel. This instability is where the need for exotic matter comes in, to prop the tunnel open long enough for something to pass through. Yet, even if we could stabilize it, the white hole end presents its own set of logical puzzles. If a spaceship were to emerge from a white hole, it would be violently expelled outward as if launched from a cannon. But from the perspective of the universe into which it emerges, that spaceship wouldn't have traveled from anywhere. It would simply have appeared, bursting into existence from a point source, its entire history up to that moment of eruption completely unknowable and disconnected from the new reality it now inhabits. White holes remain one of the most captivating what-if scenarios in theoretical physics, a beautiful mathematical ghost that haunts the edges of our understanding, challenging our notions of time, entropy, and what is truly possible in the cosmic architecture. Even as we map the grand geometry of the cosmos and grapple with the nature of time itself, some of the most compelling mysteries are found in the tiny, unexplained deviations in the paths of our own robotic explorers. A perfect example of this is the decades-long puzzle known as the Pioneer anomaly. In the 1970s, NASA launched the Pioneer 10 and Pioneer 11 spacecraft on groundbreaking missions to the outer solar system and beyond. These intrepid probes were the first to travel through the asteroid belt and make close-up observations of Jupiter and Saturn. As they continued on their trajectories into the deep, dark expanse, scientists meticulously tracked their positions using the Doppler effect, precisely measuring the frequency of their radio signals to determine their velocity and distance. Over years and then decades, a consistent and perplexing drift appeared in the data. Both spacecraft were experiencing a tiny, unexpected, and constant deceleration back toward the Sun. This minuscule sunward tug was incredibly small, measured at about 8.74 times 10 to the negative 10 meters per second squared. To put that into perspective, it's roughly 10 billion times weaker than the gravity we feel pulling us toward the Earth. It was the equivalent of the probe slowing down as if an invisible hand was ever so gently applying the brakes. This was not predicted by any of our models of the solar system. Engineers ran through every conceivable explanation, from the subtle pressure of the solar wind to the tiny amount of residual propellant leaking from the spacecraft's thrusters. For a time, the heat from the probe's radioactive power sources, the RTGs, was even considered, as photons radiating from the warm surface could provide a tiny push. But even after painstakingly modeling all these effects, a faint, anomalous signal remained, a whisper of an unknown force acting on humanity's farthest-flung artifacts. The mystery captivated physicists and the public alike as it hinted at something profound. Could this be the first measurable signature of a flaw in Einstein's theory of general relativity at the scale of the solar system? Perhaps it was evidence of unseen matter, not the dark matter that holds galaxies together, but a local, diffuse halo of dark matter surrounding our Sun, its gravitational pull subtly tugging on the probes. Other, more exotic theories emerged, suggesting it could be linked to the nature of space-time itself, a result of the universe's expansion exerting a local influence or a manifestation of new physics that would only become apparent over vast distances. The Pioneer anomaly became a classic example of how a tiny discrepancy in data can open a door to potentially revolutionary ideas, proving that some of the biggest secrets in physics are hidden not in the distant, early universe, but in the painstaking details closer to home. The case was eventually largely closed, though not without a lesson in incredible scientific diligence. A dedicated team undertook a heroic effort to recover decades-old engineering data and build the most precise thermal model of the Pioneer spacecraft ever made. Their conclusion was that the anomaly was not, in fact, a thrilling new physics phenomenon, but something far more mundane yet no less impressive: the relentless and asymmetric radiation of heat. The Pioneer probes generated heat from their electrical systems and their radioactive power sources. This heat was emitted as infrared radiation or photons. While most surfaces radiated evenly, a slight imbalance meant more heat was radiated from the back of the spacecraft's main antenna dish than from the sides. Each photon carrying away heat also carried away a tiny amount of momentum. It was this relentless photon-powered push from the warmer rear surface that was acting as a very gentle, very constant brake, providing the anomalous deceleration that had puzzled scientists for years. While the solution was ultimately found in conventional physics, the story of the pioneer anomaly is far from a failure. It stands as a powerful testament to the scientific method. It shows our capacity for relentless curiosity and meticulous detective work, even on a problem that took over 20 years to solve. It also underscores a crucial humility. Our understanding of the universe is built on measuring things with incredible precision, and sometimes the most exciting anomalies point not to new realms of physics, but to subtle details in our own engineering that we had overlooked. Yet the spirit of the anomaly lives on. It serves as a permanent reminder that as we send ever more precise probes and instruments into the void, we must remain vigilant for the next tiny, unexplained drift in the data, the next whisper from the cosmos that might truly be the first hint of a deeper layer of reality waiting to be discovered. Yet for all the universe's grand rules governing time's flow and direction, one of the most astonishing discoveries in recent years is a new phase of matter that breaks time's most fundamental symmetry right here in the lab. We are taught that the laws of physics are symmetric under time translation, meaning they should work the same way today, tomorrow, or a billion years from now. The underlying principles don't pick out a privileged moment. But a remarkable quantum system called a time crystal shatters this expectation, not by moving through time, but by moving in time, creating a perpetual rhythm without ever consuming energy. To understand how bizarre this is, imagine a perfectly smooth, frictionless bowl with a single marble resting at the very bottom. This marble is in its ground state, its state of lowest possible energy. It is completely still. No matter how long you watch it, it will not move. Now picture a different kind of bowl, one sculpted into a perfect circular track. You place the marble in this track. In a normal system, the marble would eventually roll to the lowest point and stop, just like in the first bowl. But in a time crystal, the marble, even in its absolute ground state, would not come to rest. Instead, it would begin to oscillate back and forth around the track forever, not because it has extra energy to burn, but because the very structure of its quantum reality forces it into a perpetual periodic motion. This oscillation is the heartbeat of the time crystal, a stable pattern in time that repeats with a fixed rhythm, breaking the symmetry that says a system in its ground state should appear identical at every moment. The theoretical possibility of such a system was first proposed by Nobel laureate Frank Wilczek in 2012, but it was met with significant skepticism. The major objection was that this seemed to suggest a perpetual motion machine, a system that could undergo cyclic motion without any energy input, which would violate fundamental thermodynamic laws. The key resolution to this paradox lies in the concept of a driven time crystal, also known as a Floquet time crystal. Researchers realized that you could create this stable time-based order not in complete isolation, but by periodically kicking the system with a laser or magnetic field. In a normal system, the rhythm of the system's response would precisely match the rhythm of the kicks you apply. But in a time crystal, something magical happens. The system's response becomes subharmonic. It might oscillate at half the frequency of the driving force. If you poke it twice, it only completes one full cycle. This subharmonic rhythm is incredibly robust. Even if the driving pulses are slightly imperfect or noisy, the time crystal maintains its own stubborn, stable periodicity, a clear signature that it has entered a new, ordered phase of matter. The first experimental observation of this phenomenon was a watershed moment. In 2017, two teams, one at Harvard University and the other at the University of Maryland, successfully created time crystals using vastly different setups. The Maryland team used a line of 10 ytterbium atoms, carefully arranged and manipulated with lasers. the Harvard team used a dense, three-dimensional cloud of over 1 million nitrogen vacancy centers atomic-scale defects in a diamond. Despite the different materials, both experiments revealed the same telltale signature, a persistent oscillation at half the frequency of the applied driving force, a rhythm that remained stable long after it would have died out in any other system. They had not built a perpetual motion machine. They had created a new state of quantum matter with an inherent order in time, analogous to the repeating spatial order of atoms in a traditional crystal. The potential applications for this discovery are as profound as they are futuristic. The most immediate promise lies in the field of quantum computing. Quantum bits or qubits are notoriously fragile, their delicate states easily destroyed by the slightest interaction with the environment, a problem known as decoherence. The inherent stability and rigidity of a time crystal could provide a remarkably protected foundation for building qubits. Its robust rhythm could act as a perfect internal clock, synchronizing operations within a quantum computer with unparalleled precision. Or it could serve as a quantum memory device, storing information in its periodic motion, shielded from the chaotic noise of the outside world. Beyond computing, time crystals could lead to sensors of incredible accuracy, capable of detecting minuscule variations in magnetic fields or gravity by measuring tiny disturbances in their unshakable rhythm. But perhaps the most profound implication is philosophical. Time crystals provide a tangible, laboratory-scale model for studying how time itself can break symmetry and develop structure. They offer a new lens through which to examine the very arrow of time, the emergence of causality, and the fundamental differences between the past and the future. In a universe where the most basic laws are time-symmetric, we are surrounded by evidence of time's direction, the increase of entropy, the expansion of the cosmos, our own memory and aging. Time crystals represent a new, microscopic form of time's arrow, a quantum system that explicitly distinguishes one moment from the next through its own immutable beat. By creating and studying these strange quantum metronomes, we are not just engineering a new technology, we are peering into the deep structure of temporal order itself, exploring the subtle ways in which time can crystallize into something tangible and measurable. But this relentless march toward maximum entropy and a featureless future presents us with one of the most unsettling thought experiments in all of physics, the Boltzmann brain paradox. It forces us to confront a terrifying possibility that our own conscious experience, our memories, and our entire perceived reality might be nothing more than a fleeting, random accident in a vast and ultimately dead cosmos. The paradox is named for the 19th century physicist Ludwig Boltzmann, who was grappling with the statistical nature of entropy. He suggested that in a universe that exists for an eternity, even the most incredibly improbable events are not just possible, they are inevitable given enough time. To understand this, let's go back to the idea of entropy as a measure of disorder. A state of high entropy, like a perfectly mixed gas, is statistically overwhelmingly likely. A state of low entropy, like all the air molecules spontaneously gathering in one corner of the room, is astronomically improbable, but it's not impossible. In an infinite or near-infinite universe, or over an infinite amount of time, every possible configuration of matter and energy, no matter how improbable, will eventually occur through random quantum fluctuations. This includes the spontaneous formation of complex, ordered structures. In the far, far future, trillions of years from now, when the universe is a cold, empty void nearing maximum entropy, the cosmos won't be completely still. Quantum mechanics tells us that the vacuum will still be seething with tiny fluctuations. Most of these fluctuations will be minor, creating a fleeting virtual particle pair that instantly vanishes. But every once in a while, an enormous fluctuation will occur, given enough time, and in an eternal universe, time is essentially infinite. A fluctuation could be so vast and so complex that it spontaneously assembles a fully formed, conscious human brain, complete with false memories of a past life, a sense of self, and the illusion of being in a structured world. This is a Boltzmann brain. It would flicker into existence for a mere moment, have a single thought, perhaps the thought, "I exist," and then immediately dissolve back into the featureless chaos from which it came, its energy dispersed back into the void. The terrifying implication is that it is statistically infinitely more likely for a single, isolated brain with a false history to fluctuate into existence than it is for an entire, ordered universe with billions of galaxies and a 14-billion-year history to do so. By the pure, cold math of probability, you and I and everyone we know should be these fleeting Boltzmann brains, rather than coherent observers in a long-lived, low-entropy universe like the one we seem to inhabit. This creates a profound paradox for cosmology. Our standard model tells us the universe began in a state of incredibly low entropy, the Big Bang, and has been evolving according to the second law of thermodynamics ever since. Our existence as stable observers embedded in a long chain of cause and effect makes perfect sense in this context, but the Boltzmann brain thought experiment suggests that if the universe continues forever in its current accelerating state, eventually yielding to an eternal, high-entropy de Sitter space, then our type of experience should be virtually impossible. The number of Boltzmann brains that would randomly fluctuate into existence over an infinite future would completely swamp the number of ordinary, biologically evolved brains that have existed in the universe's brief, fertile period. Therefore, if the universe is eternal, the odds are overwhelming that any given conscious experience, including your reading of this sentence right now, is a Boltzmann hallucination. This is so philosophically disturbing that many physicists see it as a powerful argument against the idea of an eternally enduring universe in its current form. The fact that we are having coherent, stable experiences and observe a universe with a clear, low-entropy past is strong evidence that the future cannot be one of endless, empty expansion where such fluctuations dominate. Something must happen to prevent it. Perhaps the vacuum of space is not stable and will eventually decay, ending the universe in a new phase transition before there's time for Boltzmann brains to form. Perhaps the nature of dark energy will change. The paradox isn't just a fun puzzle, it's a serious logical constraint that any ultimate theory of the cosmos must resolve. It forces us to ask not just how the universe began, but how it will truly end, and whether our own sense of reality is a fundamental truth or the most elaborate and tragic cosmic coincidence imaginable. But what if the very stage we've been describing, the smooth, continuous fabric of space-time, isn't the foundation of reality at all? What if it's merely a secondary effect, a collective illusion that emerges from something far more fundamental happening at the tiniest scales? This brings us to one of the most revolutionary ideas in modern physics, the notion that space and time themselves may not be primary ingredients of the universe, but could instead arise from the intricate connections between quantum bits of information. This concept finds its roots in a surprising place, the study of black holes. We've already seen how a black hole's entropy, which is a measure of its hidden information, is proportional to the surface area of its event horizon, not its volume. This was a massive clue that the information needed to describe a three-dimensional region of space might be entirely encoded on its two-dimensional boundary. It's an idea that hints at a profound holographic principle for the entire cosmos. But to build space-time from scratch, we need the mortar that binds this information together, and that mortar appears to be quantum entanglement. Imagine two particles becoming entangled. Their fates are linked instantly, regardless of distance, as if the space between them is irrelevant. Now, scale this idea up to a vast network of connections. The theory proposes that space itself, the very notion of distance and separation, emerges from the density and complexity of this web of quantum entanglement. A region of space where particles are highly entangled with each other appears to us as continuous, smooth, and connected. Where there is little or no entanglement, there is effectively no space, no connection between points. In this view, asking how far apart are these two objects is equivalent to asking how entangled are they. The geometry of the universe is at its heart a manifestation of information and its quantum correlations. This isn't just philosophy, it's a framework with mathematical rigor, most notably explored in models like the AD/S/CFT correspondence. This is a concrete realization of the holographic principle, demonstrating a precise mathematical equivalence between a theory of gravity operating in a hypothetical higher dimensional space and a quantum field theory without gravity operating on its lower dimensional boundary. The mind-bending implication is that a physicist working with the equations on the flat boundary could, in principle, calculate everything that happens in the curved, gravity-filled bulk of the higher dimensional space. The space-time and the gravity within it are encoded in the information on the boundary. They are not fundamental, they are emergent properties. To grasp this, think of a three-dimensional hologram projected from a two-dimensional film. The film contains all the information needed to create the stunning illusion of depth, volume, and perspective. The AD/S/CFT correspondence suggests our universe operates in a similar, though vastly more complex, way. The three-dimensional world we inhabit, with its gravitational forces and stretching space-time, could be a projection from a vast, two-dimensional storage layer at the edge of everything we can see. We are not just looking at the hologram, we are living inside of it, completely unaware that the dimensions we move through are a magnificent consequence of quantum information processing happening on a distant, fundamental surface. This paradigm shift redefines our search for a theory of quantum gravity. Instead of trying to quantize space-time itself, to break it down into tiny, discrete pixels, we might instead be searching for the rules that govern the underlying quantum information network from which space-time condenses. Events that seem paradoxical in a classical space-time picture, like the ability for information to escape a black hole, might find a natural resolution in this language of entangled qubits. The fabric of the cosmos may not be woven from threads of space and time, but from the invisible, instantaneous links of quantum connection, weaving together the reality we experience from the bottom up. Even as we contemplate the universe's vast, accelerating expansion, a powerful and mysterious force is actively pulling our entire galactic neighborhood in a very specific direction, warping the local fabric of space-time on an immense scale. This cosmic tractor beam is known as the Great Attractor, and its existence reveals just how much we still have to learn about the large-scale structure of our own cosmic backyard. For decades, astronomers have meticulously mapped the motions of galaxies within our local supercluster, and a consistent, puzzling drift has emerged. Instead of moving apart in a perfectly uniform expansion, our Milky Way, along with the entire local group of galaxies and the immense Virgo cluster, is all being pulled toward a specific point in the sky near the constellation Centaurus at a velocity of over 2 million kilometers per hour. This motion is far too great to be explained by the gravitational pull of any visible structure we can see. The region toward which we are streaming is heavily obscured by the dense band of stars, gas, and dust that makes up the plane of our own Milky Way galaxy, a zone astronomers call the zone of avoidance because it blocks our optical view of the distant universe beyond. It was like trying to find the source of a powerful river current while standing on a boat in a thick, impenetrable fog. For a long time, the nature of the Great Attractor remained one of the most frustrating mysteries in cosmology, a hidden gravitational heart pulling on us from behind a cosmic veil. Breakthroughs in astronomy, particularly in X-ray and radio wavelengths that can pierce through the galactic dust, have finally begun to reveal what lies in that direction. We now know that the Great Attractor is not a single, impossibly dense object, but rather the central gravitational core of our local supercluster of galaxies, which is named Laniakea, Hawaiian for immeasurable heaven. This vast cosmic structure is a filamentary network of over 100,000 galaxies, spanning 500 million light-years, and we are all part of its flow. The primary source of the immense pull appears to be an exceptionally massive cluster of galaxies known as the Norma cluster, located near the gravitational center of Laniakea. But the story doesn't end there. The Norma cluster, while massive, still doesn't fully account for the observed motion. This suggests an even larger source of gravity lying beyond it, pulling both the Norma cluster and us toward it. This deeper attractor is now thought to be the Vela supercluster, another immense concentration of mass only recently discovered because it was almost entirely hidden behind the Milky Way's disk. This reveals a universe of structures within structures, a hierarchical web of matter where galaxies form clusters, clusters form superclusters, and even superclusters are drawn toward the most massive nodes in the cosmic network. The Great Attractor is not a final destination, but a waypoint in our grand celestial journey, a dramatic testament to the fact that on the largest scales, the gravitational curvature of space-time is the ultimate architect of cosmic motion, orchestrating a flow that carries entire galaxies along rivers of dark matter toward the most profound gravitational basins in the universe. And yet, for all these rules governing the speed of light, theoretical physics has a habit of asking, what if something could break this ultimate cosmic speed limit? This brings us to one of the most fascinating and puzzling what-if scenarios in all of science, the hypothetical tachyon. A tachyon is a proposed particle that, by its very definition, would always travel faster than the speed of light. Its name comes from the Greek word tachys, meaning swift, and it represents a concept that pushes our understanding of space-time to its absolute breaking point. To grasp how bizarre this is, we need to revisit Einstein's equation from special relativity. The mathematics describes how a particle's mass appears to increase the closer it gets to the speed of light, requiring infinite energy to actually reach that barrier. For a tachyon, the equations are essentially flipped. Instead of requiring infinite energy to reach light speed, a tachyon would require infinite energy to slow down to light speed. It is forever locked in a faster-than-light state, born moving faster than light and never able to drop below that threshold. In this theoretical framework, its rest mass, the mass it would have if it were stationary, is not a positive number but an imaginary one, a mathematical concept involving the square root of -1. This doesn't mean the particle is a fantasy. In mathematics, imaginary numbers are a valid tool for describing certain properties, but it immediately signals that we are dealing with something that operates entirely outside our normal experience of reality. The most profound consequence of a real tachyon wouldn't be its speed, but its relationship with time and causality, the principle that cause must always precede effect. According to the principles of relativity, if an object or signal could travel faster than light, there would always be some possible frame of reference from which an observer could see that signal arriving before it was ever sent. This opens the door to the most troubling of paradoxes. Imagine a tachyon-based telephone. You could use it to send a message back in time to your past self, perhaps telling them not to send the message in the first place. If your past self heeds the warning and never sends it, then how did the message ever get sent to create the warning? This is a classic causality-violating paradox, a logical loop that seems to make consistent history impossible. The universe, as we understand it, simply cannot function with such contradictions woven into its fabric. The very structure of cause and effect would unravel. For decades, physicists have searched for any signature of these elusive particles. If tachyons exist and interact with ordinary matter even faintly, they could leave behind a detectable trace like Cherenkov radiation for light. When a charged particle moves through a medium like water faster than light can travel in that same medium, it produces a shockwave of blue light. A tachyon moving through a vacuum faster than light's vacuum speed could theoretically produce a similar effect. Scientists have looked for this and other signals in particle accelerator data and cosmic ray observations. Furthermore, if tachyons are a constituent of dark matter, their gravitational influence might be detectable. To date, not a single experiment has found any convincing evidence that tachyons are real. The search continues, but their absence is a powerful statement that the cosmic speed limit appears to be remarkably well enforced. So why do physicists continue to entertain the idea? Because even as a mathematical curiosity, the concept of tachyons forces us to confront the deepest foundations of our theories. They appear in various models not as physical particles we expect to discover, but as indicators that a theory might be in an unstable state. In quantum field theory, for instance, a tachyon condensate is not a collection of speedy particles, but a sign that a system is in a false vacuum state and needs to decay to a more stable, lower energy configuration. The name is used because the mathematics is similar, but the interpretation is completely different. This use of the concept helps physicists understand the stability of the universe itself. Ultimately, tachyons remain a powerful tool for thought experiments, a ghost in the machine of physics that helps us test our most cherished principles and appreciate the robust, paradox-free structure of the space-time we actually call home. After exploring the strange quantum connections and vast structures shaping our cosmos, we arrive at the ultimate question of finality. How might the story of space-time itself conclude? The fate of the universe hinges on a cosmic tug-of-war between two opposing forces, the outward momentum of the Big Bang and the inward pull of gravity, now joined by the mysterious repulsive force of dark energy. These contestants set the stage for two profoundly different endings, each with its own dramatic implications for time, matter, and the very meaning of existence. The first and currently most favored scenario based on our observations is known as the heat death or the Big Freeze. In this future, the acceleration driven by dark energy continues unchecked, forever overwhelming gravity's cohesive pull. Galaxies will be pushed apart at an ever-increasing rate, eventually receding beyond one another's cosmic horizons. Their light will become too red-shifted and faint to ever detect, leaving each island universe in permanent, isolated darkness. Inside these fading galaxies, the engines of creation will sputter and die. Stars will exhaust their nuclear fuel, with the last red dwarfs flickering out after trillions of years. What remains will be a cosmic graveyard of black holes, cold neutron stars, and the frozen cinders of dead planets, all drifting further and further apart in an expanding void. This is where the concept of entropy reaches its logical, terrifying conclusion. Entropy, the measure of disorder in a system, will have achieved its maximum value. All energy will be evenly distributed throughout the infinite vacuum. There will be no temperature differences, no concentration of energy, no potential to perform any work or power any process. The universe will have reached a state of perfect thermodynamic equilibrium. It will be uniformly lukewarm, just a fraction of a degree above absolute zero. In this state, absolutely nothing can happen. There can be no change, no events, no chemical reactions, and no motion beyond the faint, random jiggling of particles. And if there are no events, no before and after, then the concept of time itself loses all meaning. The cosmic clock, having ticked for eons, will simply stop. There is no way to measure the passage of time in a universe that is everywhere and forever the same. This is not an end in fire or ice, but in the deepest, most eternal silence imaginable, a static, finished universe where time has literally come to an end. The second grand finale is a far more violent and symmetrical alternative, the Big Crunch. This was a popular scenario before the discovery of the universe's accelerating expansion. It requires that the density of matter and energy in the cosmos is sufficient for gravity to eventually put the brakes on the expansion, reverse it, and pull everything back together. Imagine throwing a ball into the air with escape velocity. It flies away forever, but throw it with less force and it will reach a peak, stall, and fall back to Earth. In the Big Crunch model, the universe is that ball. After a period of expansion, the collective gravity of all the matter in the cosmos would begin to slow the initial rush of the Big Bang. The recession of galaxies would halt and then reverse. Billions of years later, the sky would begin to heat up as the light from distant galaxies' blue shifts on its approach. The universe would become smaller, hotter, and denser. The final act would be a mirror image of the Big Bang, but in reverse. Galaxies would merge and be torn apart, stars would vaporize, and atoms would be dissociated into their fundamental particles as the temperature soars to unimaginable levels. Space-time itself would be crumpled and curved to an extreme degree. Finally, all the matter and energy that ever existed would be compressed back into an infinitesimal point of infinite density and temperature, a singularity, much like the one at the heart of a black hole, but on a cosmic scale. In this model, time would not fade into meaninglessness, but would instead hit a literal wall. The laws of physics as we know them break down at a singularity. Just as we cannot see beyond the Big Bang, we cannot see beyond the Big Crunch. It could be the absolute end of this universe, or it could be a prelude to a rebirth. Some theories, like the oscillating universe model, suggest the collapse might not be an end but a bounce, triggering a new Big Bang and birthing a new universe from the ashes of the old, in an infinite cycle of expansion and contraction. This idea offers a strange form of cosmic immortality, though each cycle would likely erase any trace of the universe that came before it. The crucial factor that decides between these fates is the ultimate nature of dark energy. If dark energy remains constant, as the simplest models suggest, then the relentless acceleration will lead to the heat death. However, if dark energy were to decay or change its properties over time, gravity could reassert itself, potentially leading to a big crunch. There's even a more dramatic third option known as the Big Rip, where dark energy becomes so dominant that it doesn't just push galaxies apart, but tears apart stars, planets, and even atoms and atomic nuclei themselves in a final, catastrophic instant. Our current measurements point strongly toward the heat death, but the true nature of dark energy remains the greatest mystery in cosmology. The ultimate destiny of space-time is therefore not yet written. It is hidden within the physics of this enigmatic force that we are only just beginning to detect. The end of time is not a simple conclusion, but a question that pushes our understanding of the universe to its absolute limit. And so our journey through the fabric of reality comes to a close, a voyage that has taken us from the warped edges of black holes to the very origin of time itself. We've stood at the event horizon where time grinds to a halt for outside observers, and ventured into the quantum foam where the concepts of before and after lose all meaning. We've seen how the universe's ultimate speed limit isn't just a rule for light, but a fundamental property that trades motion through space for a journey through time, and how the silent, empty vacuum is in fact a seething, energetic frenzy that may be pushing the entire cosmos apart. This isn't the cold, predictable clockwork universe of the past. It is a dynamic, evolving, and deeply interconnected arena where space and time are fluid dimensions, constantly shaped by the matter and energy they contain. What makes these revelations so extraordinary is that they are not mere speculation, they are the bedrock of our modern understanding, confirmed by precise experiments and brilliant observations. The same physics that dictates a GPS satellite must correct its clock for both speed and gravity, also allows for the possibility of wormholes and cosmic strings. The theories that predict the universe's accelerating expansion also suggest the mind-bending reality of a holographic projection or an eternal multiverse. We live in a golden age of discovery where each new observation, from the tremor of gravitational waves to the subtle drift of a deep space probe, peels back another layer of the cosmic onion, revealing a reality that is consistently more wonderful and more bizarre than anything we could have invented. This exploration changes you. It reorients your place in the cosmos, not to make you feel small, but to make you feel connected to an epic story of unimaginable scale and beauty. You are a part of this universe, a collection of atoms that has evolved the consciousness to look back, to question, and to wonder at the magnificent machinery of existence. The fact that you can ponder the heat-death of the universe or the nature of a singularity is a testament to the incredible power of curiosity. The conversation doesn't end here. We want to know which of these facts completely rewired your brain. Was it the confirmation that time travel to the future is not only possible but actively happening for astronauts right now? The idea that the universe may be a holographic projection, or perhaps the haunting thought experiment of the Boltzmann brain? Share your number one mind-blowing moment in the comments below. We read every single one and love seeing these discussions take on a life of their own. If this journey through space-time has left you hungry for more, you're in the right place. We're constantly exploring the furthest reaches of science, from the mysteries of dark matter and dark energy to the search for life beyond Earth. Make sure to subscribe and hit the bell so you don't miss our next adventure into the unknown. The cosmos is the greatest story ever told, and we're just beginning to learn how to read it. Thank you for joining us, and until next time, keep looking.